couple more examples of these Bernoulli equations, and hopefully you had an opportunity to work through these. This one's an initial value problem. So we have square root of y prime plus square root of y cubed is equal to 1. To put it into the Bernoulli form, we have to isolate the differential term, the y prime. So we're going to start by dividing everything by root y. And when we do that, obviously, first term is y prime. The second term, y cubed over y, becomes square root of y squared. Square root of y squared is just y, so that makes it really nice. And then finally, on the right-hand side, this just becomes y to the minus 1/2 power, because we have 1 over root y. So clearly this is a Bernoulli equation, because we have this nonlinear term, this y to the minus 1/2. And so let's let v be equal to, and we know that's Bernoulli with n equals minus 1/2. And so remember that v is equal to y to the 1 minus n, or y to the 1 minus 1/2, 1 minus negative 1/2. Or in other words, v is going to be equal to y to the 3/2. If we raise both sides to the reciprocal, which is the 2/3 power, v is to the 2/3 power is going to be equal to y. And now we can go through and we can do the substitution for y prime as well as y. So we're going to now find the derivative. Derivative of v to the 2/3, 2/3, not 1/2, but so that's going to be 2/3 v to the minus 1/3 dv dx is equal to the derivative of y, which is y prime. We're going to substitute back in, and we're going to hope that this makes it a linear differential. So we get 2/3 v to the minus 1/3 dv dx. Remember that y was equal to v to the 2/3, and that's going to be equal to v to the 2/3 to the minus 1/2 power. I'm going to keep, for some reason I don't want to write my fractions correctly today. Don't know what's going on. So that's minus 1/2 power. All right, now we're going to simplify this just a little bit. So let's go down here, and we're going to rewrite this. We know that v to the 2/3, we're going to multiply that. So ultimately we wind up with this differential, 2/3 v to the minus 1/3 dv dx plus v to the 2/3 power is going to be equal to, when we multiply that, that becomes v to the minus 1/3 power. We're going to divide everything by 2/3 v to the minus 1/3 power to isolate that first term. So 2/3 v to the minus 1/3, 2/3 v to the minus 1/3, 2/3 v minus 1/3, and we end up with a nice linear equation. So dv dx plus 3/2 of v. Right? So we have 2/3 minus a minus 1/3 becomes 3/3. And then on the right hand side, 3/2. And I don't think we can get an easier linear differential for this one. Right? So this is linear at this point. P of x is 3/2. Q of x is also 3/2. And our integration factor is e to the integral of 3/2 dx, or e to the 3/2 x. We're going to use our formula to be able to solve for v. So v equals 1 over I, which in this case is e to the 3/2, times the integral, 3/2 x, excuse me, integral of q of x, which is 3/2, times I, which is e to the 3/2 x plus c. Taking the antiderivative, because we have a linear in that exponent, we can use the reverse of the chain rule. So v is going to be 1 over e to the 3/2 x times 3 halves e to the 3 halves x divided by 3 halves. Right? So remember, reverse of the chain rule, we don't multiply, we divide, as long as the term is linear, plus c. And now we can see how easy and how nicely this works out. V is 1 over e to the 3 halves x. 3 halves are going to cancel, so we have e to the 3 halves x plus c. We can distribute, we can also back substitute for v. Remember earlier, v, all the way back up here, was y to the 3 halves. Right? So v is y to the 3 halves power. So we're going to have y to the 3 halves is going to be equal to, if we distribute, these are going to cancel the first two terms, so that's just going to be 1. And then we wind up with a c over e to the 3 halves x. Right? And then we could raise both sides to the 2/3 power to solve immediately for y. We can't distribute that 2/3 power. So y is going to be equal to the quantity of 1 plus c over e to the 3 halves x to the 2/3 power. And we can leave it like that. No reason to try to doctor it up anymore at that point. All right, so we've seen a couple examples of being able to work with these Bernoulli equations. Oh, by the way, this one was an initial value problem. I forgot about that. So let me go ahead and finish this off. Y at 0 is 4. So we're going to have to solve for c. So 4 is going to be equal to 1 plus c over e to the 3 halves times 0. Thankfully it was 0 and not anything else, because that would be ugly, to the 2/3 power. All right. This just becomes 1. We'll make a little more room here. And we're going to have to raise both sides to the 3 halves power, so 4 to the 3 halves power is going to be equal to 1 plus c. 4 to the 3 halves should be 8. 8 minus 1 is 7. All right. Certainly check that with your calculator just to verify. But square root of 4 is 2. 2 cubed is 8. 8 minus 1 is 7. And so our our particular solution, we're just going to take it, we're going to substitute for c all the way back up here. And so y is going to be equal to the quantity of 1 plus 7 over e to the 3 halves x to the 2/3 power. All right, so just like every other linear differential we've seen so far, or first order differential, we've seen that we can find the initial value for those as well. All right, so one last example, and we have this y prime minus y to the minus y over 3x equals e to the x y to the 4th power. All right, so immediately we recognize this as a Bernoulli equation because we have that y to the 4th power. All right, so again, as soon as you see that nonlinear term, think to yourself it's Bernoulli. N is going to be 4. So that means that v is going to be equal to y to the 1 minus 4, or y to the minus 3 power. And then at that point we can raise both sides to the negative 1/3 power to solve for v. So v to the minus 1/3 is going to be equal to y. We can take our derivative, so we're going to hold on to this because we're going to need that. Our derivative, negative 1/3 v to the minus 4/3 dv dx is going to be equal to y prime. That's a 4/3 in English. All right. So now we can substitute for everything. Right? So when we substitute, we're going to get minus 1/3 v to the minus 4/3 dv dx minus, now I'm going to separate this y. So remember, y was equal to v to the minus 1/3. So we have v to the minus 1/3 times 1 over 3x. Right, and right here is that 1 over 3x. And then finally, that's going to be equal to e to the x times v to the minus 1/3 to the 4th power. All right, and that's right here, being able to substitute in. Now we're going to divide everything, and hopefully this is going to work out really nicely, as it has in the last two examples, and I believe it will. So if we divide everything by negative 1/3 v to the minus 4/3 power, and then we're going to divide that by minus 1/3 v to the minus 4/3. Let's just be careful when we do this. So this just becomes dv dx, which is nice. We have a negative and a negative, which becomes a positive. This is just going to become v, and then we have a 1 over x, so this is going to become plus 1 over x times v, I believe. All right, because we have a 1/3 divided by 1/3. We still have an x in the denominator. That doesn't go away. And then we have negative 1/3 plus 4/3, which becomes 3/3 or 1. And then on the right-hand side, these v's are going to cancel out very nicely. And I believe we're going to be left with a negative 3 e to the x. All right. And that's a very nice linear differential at this point. All right. And that's what happens with all these Bernoulli equations. They turn themselves into very nice linear types. So we have our p of x, which is 1 over x, which is really nice. We have our q of x, which is minus 3 e to the x. And then our integration factor is e to the integral of 1 over x dx, which is e to the ln of x. Technically it's absolute value, but we're just going to forego that. And we know that e to the ln just becomes x. So we're going to multiply everything by that. And so our v for our formula is going to be 1 over I, which is x, times the integral of q of x minus 3 e to the x times I, which is x, plus the constant c. And there should be a dx in there. All right, so let's just focus on evaluating this integral now. All right, and the integral that we have is negative 3x e to the x dx. To be able to evaluate that integral, we have to do it by parts. There's no other way to do that very nicely. So we're going to say u is going to be the factor that's going to reduce in order. Let's call u negative 3x. And v is going to be the remaining factor, e to the x dx. Or dv, excuse me. And so du, which is the derivative, is negative 3 dx. And then v is just going to be the antiderivative, which is e to the x. All right, so we've seen this one a few times, so hopefully as we go through it, you become more confident in evaluating this. So our v, by using our formula, and just in case you don't remember the parts formula, uv minus integral v du. And this v, by the way, there's two different v's going on here. I probably should have used a different variable. But this v is the original substitution of v. All right, so I probably should have called that v1 or something like that in retrospect. But hopefully you all get the idea that we're just integrating what's inside. So that's going to be 1 over x. And from our parts formula, uv is going to be negative 3x e to the x minus the integral of v du, which we can write as negative 3 e to the x dx. And then we still have that plus c. And then finally, we just evaluate this integral which is left over, a really basic one that's just positive 3 e to the x. So our v is 1 over x, negative 3x e to the x, plus 3 e to the x plus c. And then finally, we can go ahead and we can substitute for v again. Remember, v was y to the minus 3rd power. All right, so all the way back up here, we said v was y to the minus 3. And unfortunately, this is our not so nice answer. All right. If we wanted to get an explicit version of the solution, we could just raise both sides to the minus 1/3 power. So you can keep it like that, or another way of writing it, if you really wanted to, although I wouldn't suggest it, you could distribute the x, and we could just raise this to minus 1/3 power. But if you wanted to keep it as the first one, that's perfectly fine too. So as we've seen, substitution is more rigorous than the other methods that we've seen thus far. However, it does work just as well as the other ones, but just requires a little bit more care as we're doing the algebra and calculus.